Welcome, everybody. Thank you so much for joining us today. A couple of housekeeping items before we really get started. I just want to remind you that there are some accessibility and language options available in the top right corner of the event portal. And there is a chat box, which is where we're going to be doing most of our communicating back and forth, so we can make this a little more interactive. I've learned if you're on full screen, you may not be able to see the chat box options. So you may want to, if you can zoom into like 90%, then you should be able to see it or more. And then anytime, please drop a question or comment in the chat box. We're doing our best to monitor it as we go along. And with that, we will really get started. So my name is Erica Swinimer. I'm a junior high mathematics coach with the HRCE, and my co-presenter today is Suad Ashkar, who's also a junior high mathematics coach with the HRCE. And what we're going to be exploring today is inquiry-based teaching through 3-act math tasks. So 3-act math tasks are math problems that generate curiosity and foster engagement through contextual narratives. So as you can hopefully see on your screen right now, we have some learning goals in mind for today. So we'd like for you to experience what a 3-act math task could look like. We want to unfold the teacher moves behind each of these acts. We're going to share some resources for you to create or where you can find some. And then woven throughout it all, we are going to be talking about the role of a 3-act math task in an inclusive classroom. And with that, I'm going to turn it over to Suad so we can dive right into our first task.
All right, welcome everyone again. To get started, it would be great if everyone can go to student.desmos.com, maybe on new tab or new window, whatever works best for you, and enter the code you see on the screen. Once logged in, your screen should look like what you see here on the right. I'm just going to wait a little bit and see if there are any trouble logging in. I believe at this time, Erica has dropped the Desmos link as well as the code in the chat box. So once you're logged in, your screen should look like what you see here on the right. We'd like to invite you to take a moment and look at the picture and answer a few and write a few statements about what you notice and wonder. Sorry.
It's great. Just taking a look at the dashboard. So we have one person in. So we're working with this 10-second delay. So we're trying to feel our way around that. So we'll wait a little bit longer.
All right. So just want to say that once you're logged in, feel free to write a few statements about what you notice and wonder about the image you see on your screen. What you share on Desmos today is going to be anonymous as we turn the anonymous feature on. Desmos has a great feature where your names would not show up, but names of Nobel mathematicians will actually show instead. We'll give you about 3 minutes or so, or however many minutes you would need to just fill this out. And a friendly reminder, please do not close that Desmos tab as we will be going back to it later on. If you have any difficulty to log into Desmos, forget about Desmos and just like drop what you notice and wonder in the chat box here, and I'll monitor this as well.
Here we go. We're starting to get some people in the Desmos. I see 7 people in, getting some of our notices and wonders being typed in. So that's great. Thanks, everybody.
I don't see anything in the chat so far, so I'm assuming Desmos is working.
Oh, this is great. Lots of noticings, lots of wonders. I'm going to give you about 10 seconds to just sort of finish your thought. No worries if you didn't get everything down, or if you didn't finish, that's just fine. Okay, I'm going to use one of my almost favorite feature of Desmos. I'm just going to pause everybody. And at this point, I'll invite you to join us back in the event portal. And reminder, just keep that Desmos open because we'll be back and forth in it over the next hour or so. And then I just want to share some of the things that we've noticed. So it's a continuous loop. There are 12 knots. The knots appear to be equally spaced. There are 12 knots, infinity shape, closed loop. There are knots at intervals. The knots seem to be at equal intervals. It's a rope with knots. The rope seems to be laid out in a specific shape. 12 knots, a continuous rope with 12 knots. I see 2 circles and a square. All right. And then what are some of the things we're wondering about? What's the distance between each knot? How long is the rope? Is this an inside or outside the circle activity? Why? Are the knots equally spaced? What are the knots for? What is the shape for? And finally, why would someone place 12 knots equally spaced in a rope? Amazing.
These are great notices and wonders. And so we're going to be answering some of your questions. To answer some of this, we're going to give you some information. So this picture, the picture that you saw represents a rope that is actually divided into 12 equal intervals. Somebody has noticed that. This is great. They are separated by knots, and that's what you guys also observed. Now, somebody asked, why is it's in a certain shape? Why is this shape the way it is? Or are they equal? Yes, we said they are equal. Somebody asked, what is it used for, and why would anyone separate this the rope into 12 equal knots? So some sources believe that knotted ropes were used in the Middle Age to help build and create geometric shapes, including triangles, circle, and rectangles. It is believed that in ancient Egypt, surveyors, known as rope stretchers, used knots or knotted ropes to create right angle triangles. Now that we know a little bit about what this is, we would like you to use this knot to make right angle triangles today. Now in the classroom, I would take time to review what a right angle triangle is, but for today's sake and knowing that you may be all math teachers, we're going to just ask you to create right angle triangles. Since this is a virtual event and using a physical rope is really practically impossible, we created a model on Desmos that we would like you to manipulate and try to create a right angle triangle using this rope. So the next thing I'm going to do is show you how this works. All right, the following is a model of a 12 knotted rope. Each movable point, red and blue, represents a knot. Although there are 13 points right here, the beginning and end points should overlap at the end to represent a single knot. As mentioned before, the distance between each knot is the same. Now, usually it is best to let students explore how the model works, but in the interest of time today, we're just going to ask you to start with the red dot. If you move the red dot, you can move the entire model. Each blue dot rotates around the dot before it. So we'd like to invite you to try to move these dots so they create a right angle triangle. You are to use the entire rope with no crossing over. The red dot and the last blue dot should overlap at the end. If you find a triangle, we want to invite you to try to find another one on the next slides. There are 5 and 6, slide 5 and 6. Try to play around there. And do not forget to share with us your dimensions of that triangle. Also, feel free to explain how do you know it's a right angle triangle. Now, I'm going to invite you at this point to go back to the Desmos tab and try this. We're going to give you about 5 to 7 minutes, And we're going to regroup back here. We're going to pause the activity like we did and regroup back here. Another friendly reminder, please keep that tab of Desmos still open because we may go back to it later on. If anyone has any questions or is having any difficulty, also the chat here is perfect for all your questions, and we can help you with this.
Great. Looks like everybody is in and starting to play around with the model. If you don't know Desmos, this was one of the reasons we chose it, is that we're able to see what's happening through the teacher dashboard. So as you are working on it, we're able to see what's happening, which is a great feature of this.
I hope you are finding that model easy to use, to create, or somehow easy to use. We did our best. All right, a friendly reminder that if you've already done a triangle on slide 5 and you did write down the dimensions, probably explaining how you know it's a right angle triangle, try one on slide 6. All right, Erica, where are we in terms of?
I think we'll give another minute. I think there's a few people still who are just moving on to slide 6.
All right.
Okay, so I'm going to give you about, say, 30 more seconds. Again, as before, please don't worry if you haven't quite finished it. About 30 more seconds to finish up what you are working on. Okay. So I'm going to pause you again and invite you to join us back in the event portal. Here we go. Okay. So I'm just going to stop sharing this and jump into here we go. So you're getting a little peek at sort of the dashboard piece of it. So one of the things that we can do with Desmos, as I mentioned, is sort of see what you're doing as you are doing it, but I can also take snapshots. So they're anonymous, no names attached to it, and it just kind of gives us an idea of what we were working on. So these first two just came as we were starting. So you can see they are on their way to becoming right angle triangles. Definitely a bit of a learning curve with this model as you try to manipulate kind of one dot and then all the others seem to move. So then we were successful. We got some right angle triangles here. And then here are some of the dimensions from that first one. So a lot of 3, 4, 5. It's a 3, 4, 5 right triangle. Also use the grid lines for it. A right angle triangle or a 3, 4, 5 triangle. And then for the second one, we had the same triangle. So it had the same dimensions, but there was a rotation. And then we have this one here. So this time, instead of saying 3, 4, 5, we end up with a 6, 8, 10. So I'm hoping that maybe in the chat, someone could maybe share with us what they were thinking, what they, any observations or sort of the process they went through, or want to say anything about any of these, any of the work that our group has done.
Okay, there's a little bit of delay here. I think we're good to move to the next slide. And if people say anything in the chat, I'll read it back for you. So as you may have noticed all, if we look at the first graph, right? Oh, I'm going to wait for Erica to share first.
Sorry.
The screen. You know, this 10-second delay is...
Yes.
Yes.
There we go.
All right. So if you look at those two triangles that we made. These are some possible solutions. You can see that you may or may not have noticed that it's not any dimension that would create a right angle triangle. If you look at the first graph to the left, we can see that each two small squares are equal to 1 unit as the graph is actually labeled. So if you were successful at creating a right angle triangle, the model here, you should have a triangle with a leg of 3, another one of 4, and a hypotenuse of 5. The orientation may be different, but the triangle is the same with the same dimensions. The graph to the right is not labeled, but if you consider that each small square is equal to 1 unit, we would have a triangle with dimensions which are 6, 8, and 10, like somebody has already figured that out in the solutions. So at this point, we would like you to look at the two sets of dimensions, the 3, 4, and 5, as well as the 6, 8, and 10, and probably let us know, what do you notice about these two sets of dimensions in the chat, if you don't mind. Just somebody let us know what is something that you actually observe or notice about these two sets of dimensions, 3, 4, 5, and 6, 8, 10. Somebody is saying there are multiples of 3, 4, 5. Yeah, the 6, 8, and 10 is multiple of 3, 4, 5. And it's, yeah, 3 times 2 is 6, and 4 times the dimensions are doubled. Yes, is another observation. Great. Related by a factor of 2. This is great. They were all doubled. This is true. Now, as math teachers, we all know that a set of dimensions that is a whole number creates a right angle triangle is referred to as Pythagorean triple. The idea of this task is to introduce what Pythagorean triples would be by letting students experience this through a 3-act math task. At this point, I guess what we went through today is a 3-act math task. The first act, Erica will be unfolding this for everyone and then see what we did, what are the teachers' moves that we actually went through, and how this can be extended later on.
Okay. So as we mentioned, we want to be able to unfold these and sort of show you where each of the acts were and what happens in each act. So the first act of a 3-act math task is where we establish the scenario. We're creating a narrative conflict or tension. It can be a movie, a statement, a fact, an image, anything that stimulates the student's interests. What's really important here is that this first act has to be accessible to everyone in the classroom. So in the task we just did, this was our notice and wonder. So a notice and wonder is a great way to get every student in your class to share. It's okay if they notice that the rope is laying on boards. It's okay if they count the number of boards or if they look at the colors. These are all things that can be noticed or things that they can wonder about. And the more they share and the more they realize that what they're sharing is accepted and respected, the more willing they become to share, and we can get into some of those deeper math concepts with it. When we're showing something like this, we want to be generating curiosity. We want to be fostering engagement, and we want our students to be the ones doing the thinking. So that's all that should be happening in that first act.
All right. And right after we ask you what you noticed and wondered, our Act 2 consisted of providing you 2 pieces of information. One, we give you information about the rope, what it is, what it's used for, as well as we gave you another opportunity to actually play with the model virtually to create your own right angle triangles and experience doing it hand-on. Now in the classroom, this can be done also through virtual, like through Desmos, but it is also a good idea to have an actual rope that the students can manipulate, perhaps in groups of 3, and pretend they are rope stretchers, like in the Middle Ages, like early on. In our second act, we build the story by adding new elements and pieces of information you could use to come up with a solution. When teaching in person, it is best if students work in groups and collaborate to come up with a solution using different strategies, as well as bringing their own individual mathematical strength. At this point, teachers will provide hints and instruction as needed. We try to give you a hint on slide 6 that the graph is not labeled. Can you find something else? You may want to hide this information and let the kids do the task without that information, and maybe drop it later on if you see them struggling, not finding a new triangle. And it is worth noting that at any point of this task so far, whether it's about the notice and wonder or about manipulating the rope or its model, the whole task is accessible to anyone in the classroom. There are no pre-required mathematical knowledge that they need to be able to create right angle triangles, unless if they don't know, or if they know Pythagorean. But by this time, we talk about right angle triangle and Pythagorean theorem. They've seen that before. This is the knowledge that they have seen right before this task. Or if they have never seen this and you want to introduce Pythagorean theorem with this task, if they know what a right angle triangle forms 90 degrees, they would be able to see this on their screen without any knowledge of what works and what doesn't work as well. This is Act 2, I think. Now we're going to move to Act 3.
Okay, so we move to the final act, to Act 3 of our 3-act math task. Here we want to resolve the conflict and reveal the solution. In this act, students are given the opportunity to share their solutions and methods. This is where with our task today, we took the snapshots and we shared the pictures with you. In the classroom, it would have been, we would have been able to ask students what they did as they went through it, what they struggled with, how they came up with the solution, how they maybe came up with the second one. And then the third act also gives an opportunity for teachers and students to celebrate the mathematical thinking behind their solutions. And as well, it presents an opportunity for students to make connections and extend the content. The diagram that you see here is from Jeff Kral's book, Necessary Conditions. And it does a great job of simplifying in one image what a 3-act task is. So we have Act 1. We're establishing the conflict and we're posing the problem. So in our task, this was the notice and wonder. In Act 2, we have the struggle and the exploration. It's not a straight line. We're not moving from A to B. Sometimes seem to be moving backwards or all over the page. That's okay. In this part, in Act 2, students are working collaboratively. The teacher is there to give instruction or hints as they are needed. And then we move to Act 3, where we have our resolution. So we've reached the solution and we have completed the story. So if we look at stories as sort of having that, intro to the conflict, the working through it, and then the resolution, we can also have sequels. And so for a 3-act math task, they can have sequels as well, and these are extensions. So what we thought was a good extension for this 3-act task that we had done was to check what other numbers of knots could you use to make a right angle triangle. So instead of providing the model for them, we can give them a sketch pad where they can create their own knotted rope, and they can determine how many knots they would need so they can explore. We gave them a 12-knot rope, so what if it has 13? Would that work? How about 14? And hopefully they can explore and find other ones. So they might find those multiples that we talked about, like 6, 8, and 10, or maybe they'll find one for another family of Pythagorean triples, so maybe a 5, 12, 13. Might also be interesting to introduce scale factor in other grades, making the connection between the concept of those multiples of numbers and their relation to similar right angle triangles. Alternatively, the use of a knotted rope by ancient Egyptians remains a controversial topic, as some believe that its use has never been documented. So students may want to look for other tools used throughout history that have connections to math. So in the interest of time, we're not going to send you back to Desmos to do this, but we will share the Desmos with you at the end. So if you wanted to go back at any time, you can feel free to do so.
All right, so the task that we just worked on is an adaptation of a question on page 45 in the grade 8 math textbooks that we use here in Nova Scotia. It is worth noting that in his book, Building Thinking Classrooms in Mathematics, Peter Liljedahl makes an interesting observation or distinction between what we call curriculum tasks, like the one we see in textbooks, and problem solving. He states that problem solving is usually what we do when we do not know what to do, whereas a curriculum task, like the one we see in textbooks, students often do those tasks when they know what to do after we've told them how to do it. To make the question in the textbook one where students get to do the thinking themselves and using a model and having it more engaging and interacting, we decided to remove all the information this question is providing. The only thing we really kept was the image. Well, we actually recreated it, thinking that some of you may recognize that image. By doing so, we gave you, the attendees, the ownership of that task. And we were there to, you were the ones asking the questions, and we were there answering your questions as needed while giving you guided information of how to move forward. Like, this is an outcome, this is a gradient outcome. This is students are expected to develop and apply Pythagorean theorem to solve problems. And in Nova Scotia, the indicator MO105, this is about solving problems that involve Pythagorean triples. This is where we're connecting this to the idea of outcomes here. Before, no. Okay, so if we look at the task that is in a textbook, and we look at the task that we just did today, I'm going to invite you to think about which of the two tasks sparks more curiosity and engagement in the classroom, promotes accessibility to all for all students, goes beyond the arithmetic one solution that we're looking for, promotes conversation and discussion, and connects to real life. Also, can be extended. We can extend the content. I'm going to invite you at this point to feel free to share what your thoughts about what we've done so far. Do you agree? We were hoping that you agree that the task, that the 3-act, this question turned into a 3-math act task is more engaging, and you agree that it actually fulfills all of those criteria. Before we move on to the next task, if you have any questions about, or if you have any comments about what we've done so far, please feel free to put them in the chat, and we will answer all your questions or comments, address them. All right, so I guess we're good to keep going.
I don't want to cut anybody off. Please feel free. We are watching. So if if we move on, if there's anything, please feel free to add that to the chat. But we do have another 3-act task that we were hoping to go through. It's done a little differently, so we just wanted to show you there's not like one model and they all must follow this way. 3-act task, because the 3 acts and how we present the information can change. So this one is called Twinkie. And here's your starter. A dog named Twinkie is trying to set the Guinness World Record for the fastest time popping 100 balloons. We'd like to know, how long will it take the dog to pop all 100 balloons? So our starting task this time is going to be an estimation. So we'd like to see an estimate that's too low, what's too short a time to pop 100 balloons, an estimate that is too high, and then your best estimate. So again, I'm going to unpause the Desmos, and if you don't mind flipping back to that tab, and you'll see that you can enter your answers. If you choose to click the Share with Class button, you are still anonymous, so you will be sharing your answers, but you'll share it under an anonymous name, and then you will see what other people have also looked at. So if you want to jump on over there. Okay, so we're getting some too low estimates. We've got a few 10 seconds are showing up as too low. 5 seconds, another 10 seconds. 3 seconds is too low an estimate. Okay, yeah, 25 seconds is too low. All right. And then if we start looking at our too high, we've got 1 hour, a couple of times in there. Yep. 5 minutes or 300 seconds, that's too high. 10 minutes or 4,000 seconds. All right. Great. And then as we start to sort of narrow it down and think what would be reasonable, we've got a couple of people thinking that 2 minutes. 2 minutes is a reasonable amount of time, so 120 seconds or 100 seconds. We've got a 45 seconds and we have 50 seconds. Okay, so this was Act 1. We're setting the stage. We're presenting a question. It's accessible to everyone. We've made it an estimate. Hopefully we've kind of sparked your curiosity, what's happening with the dog and these balloons, fostering some engagement. So we've got lots of answers here. And our students are the ones who are doing the thinking. So let's move on to Act 2. So remember that in Act 2, we want to add more to the story. We're going to give a little more information. So in this case, we've chosen to use an image. So we can see Twinkie here among all of these balloons, and we have a couple of numbers, so some information on here. So in the classroom at this point, you might get your students, so they're working in groups, right? This is the collaborative part of it. You might get them to maybe do another notice and wonder about this picture. Maybe ask them, what information do you see, or what information would you need? I think there should maybe be some questions about this number up here. What does it represent? Is it time? Okay, if it's time, is it hours, minutes, seconds? What are we talking about here? Again, in the interest of our time this morning, I will let you know that it is time and it is 5 seconds. So what we can see is that in 5 seconds, Twinkie has managed to pop 25 balloons. So I think either way, if you want to go back into the Desmos and type your answer, if you want to drop it in the chat, if that is easier instead of flashing back and forth. With this information, how long do you think it's going to take Twinkie to pop all 100 of these balloons? So wherever you want to put that information, we have both of those things open.
Yeah, at this point, you can change your estimate or just keep it as is based on the information you have.
Okay, so starting to get some answers here. All right, so we've got 25 seconds, 20 seconds, 30 seconds, another 30 seconds, 22 seconds. Five minutes. I think I said 25, another 20 seconds. Okay. Excellent. All right, so Act 2, we add a little more information. Our students are, it's still accessible to all the students. They're collaborating on a solution using multiple approaches, and then the teacher can give hints like I did with telling you it was 5 seconds or instruction as it's needed. So I'm going to, just so you don't have to keep jumping back and forth, I'm going to show you the next page on Desmos. There we go. So that should show you the same image that we're presenting in the meet, but I've paused you, so you can't enter anything just yet. So we're doing a second Act 2. So we want to give a little more information. And here we find that this has actually been done before. So Mitch and Callie, the Wonder Dogs, have actually burst 100 balloons with a time of 41.67 seconds. So we're now giving you a second piece of information. And so we would like to know, will she beat that old world record? So I will unpause you, and then you can go ahead and let us know, yes or no, is she going to beat that old world record? I got a yes, a yes, a yes. I got to go Twinkie. Yes, I think we're all Team Twinkie here. We are cheering Twinkie on. Yes, 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 yes. Check my screen. Another yes. Yes, I think so. Awesome. Okay, so see, there's that fostering, sparking that curiosity. We might at this point, you know, when students have made this decision, we could turn around and talk about it. We could say, now you've had these two pieces of information. So did it change your answer? How did it change your answer? So lots of things to explore here. So we're going to move on to Act 3, and I'm going to do the same thing up here in, there we go. I'm going to pause you. So same. So again, you're looking at whether you're in Desmos or back in the feed loop, you're looking at the same picture. So this is our Act 3. Remember, in Act 3, we want to provide a resolution to our conflict. We want to know if Twinkie is actually going to beat this world record or not. So before showing this in the classroom, this is where students get to share what they've done, what their solution is, how they reached it, how they worked together, how they used the information that we gave them, all of these pieces together. So let's find out. I just need to switch how I'm sharing here. Oh, no, we can't see it yet. Wait. Hang on. Let's restart that. Okay. Make sure everybody can see the fun. All right, let's try this again.
All right, so yes, Twinkie did actually beat the world record, and it is 37 seconds. He did this in 37 seconds. Anyhow, so if you look at the graph here, one would think that with the first bit of information that we got, 5 seconds, 25 balloon, one would think that Twinkie would be able to actually pop all 100 balloons in 20 seconds and think about this as a linear relationship. However, the graph shows, the graph that you see right here on your screen shows that this is really not a linear relationship, as there are so many factors that interfere with Twinkie popping the balloons. This task is great when you're introducing probability rate in grade 8, but it also can be used in higher level higher level math classes to introduce non-linear relationships. It can also be introduced or done when introducing linear relationships and talking about other factors in real life that may not make the relationship going or the rate going at a linear rate. As we can see here, I do not know if you notice. I think Twinkie will take much more time had the balloons not been all taped probably to the ground. We don't know if they are, but they're not moving once he moves around them. They seem to be just stable. There are so many factors to discuss with students, so many real context that you can actually discuss with students when you're doing these tasks. So speaking of this, I'm just going to give Erica just a second to share her screen and show you what an alternative question in a typical question in a textbook could be. It could be, a dog named Twinkie pops 25 balloons in 5 seconds. How long will it take the dog to pop all 100 balloons? Without a context, this question is only looking for the arithmetic solution and may not be accessible to all students. It presents a single solution without taking into consideration the factors that could influence its results, as we've seen in the video. Students at this point may solve this question without even thinking of or even questioning, why would a dog need to pop 100 balloons, and why would he do that in 5 seconds? 3-act math tasks are tasks that are related to real life. They have a context and present mathematical features or relationships that students may wonder about. This is important so that we do not end up with memes that look exactly like this one.
So speaking of wondering why, as we come to the end of our time, we wanted to share our why with you, why we choose to use these types of tasks and why we feel they are so powerful. Hopefully you've seen the context piece of this, that using the mathematics in context makes a stronger connection for our students with the work that they are doing. But we also like these tasks because they're low floor and high ceiling. Low floor meaning that they have an easy entry point that's accessible to our students. Accessible to all students. We use the notice and wonder task as well as the estimation in the 2 that we did. These types of tasks allow all students to feel that they have something to add to the math classroom. High ceiling refers to the fact that there's room for complex math as well as extensions, such as other Pythagorean triples or what makes a graph nonlinear. The tasks that we've shared today are a type of guided inquiry where the students are doing the thinking and the teacher is there to support as needed and to facilitate the sharing of ideas and solutions. We also want to make sure that you have access to the many, many resources that are available. 3-act math tasks were first started by Dan Meyer a few years ago. That's where the Twinkie one came from. He shares a collection of these on his blog, so we have given you through the Desmos a link to all of these, so his Twitter account as well as his collection of the tasks. And there are more 3-act math tasks available from lots of people. We've chosen a few to share with you, and we've included some French resources, which you can also see listed on the screen. Just a friendly reminder that the above resources may not necessarily align with our Nova Scotia mathematics curriculum, so please keep that in mind. And we are just about at the end, so we wanted to say thank you so much for joining us. Our contact information is here. Please feel free to reach out if you have questions or comments. And finally, we just have a little bit of feedback that we'd love to hear from you about. So again, in about very shortly, I'm going to send you back to that Desmos, and we would love it if you could choose one of the prompts that are there and let us know how you feel about today's presentation. So it could be a thing that we could do better, one thing you want to make sure you don't forget, a light bulb moment, or something you might still have a question about. And I believe within the event portal itself, there is an engage button, and it will be active as long as we are active, so about another 7 minutes or so. So you can also fill in, I think it takes you to a Google form. So there's a feedback form there that you can fill in. And I believe there's supposed to be a link to it later if you miss out on it once we are no longer live. So I will unpause that Desmos so you can actually type in there. And we're here, we'll be here till noon, so please feel free to throw a question in the chat or a comment, whatever it is, and we'll make sure to share that Desmos with you in the chat.
Yep. I'm going to drop this right now.
Perfect.
The link to the Desmos presentation. Our whole presentation was done in Desmos, so if you want to do it with your students, make sure you make a copy and delete whatever the slides that you do not want your students to see. Just edit it.
thanks again, everyone who came and for filling in some of the feedback. Please don't feel you need to stick around, go a little early for lunch, but we will be here for like 3 more minutes just in case maybe a question or comment comes through that chat. But yeah, thank you again for coming.